Hello everyone, welcome to this new seminar from the Instituto de Astrofísica de Andalucía. Today we have the pleasure to have the talk by Luis Alberto Díaz García. So Luis made his PhD at the Centro de Estudios de Física del Cosmos de Aragón, the CEFCA, in 2017 as part of the Alhambra and JPAS collaborations. And between 2018 and 2020, he was a postdoctoral fellow at the Academia Sinica Institute of Astronomy and Astrophysics in Taipei. Since mid-2020, he is a virtual postdoctoral fellow here at the IAA, working with the Stellar Population Group. And here he works on data validation tasks and galaxy evolution researches in the miniJPAS survey. So during his career, he has participated in many galaxy evolution studies, contributing to the study of stellar population properties of galaxies, formation and evolution of galaxies, stellar mass and luminosity functions, galaxy mergers, and many other topics. So today he will be talking about stellar population studies in the JPAS survey. So,
okay, thank you very much for the introduction. So, first of all, thanks for attending this seminar. And also, at any time during this seminar, if you have any question, don't hesitate to raise your hand for making a question or whatever. For me, there is no problem. And also, now, during this seminar, I'm going to present part of the stellar population studies that we are doing within the JPAS collaboration. And in particular, I will focus on those stellar population studies in which I have participated more actively, as well as those that the ones that I have led within the JPAS collaboration. So during the seminar, I start the seminar with a brief introduction of the JPAS survey, as well as the techniques that we have been performing in order to constrain the stellar population properties of galaxies. Later, I also introduce part of the scientific results that we have obtained within the JPAS collaboration, of course, about the stellar populations of galaxies. Later, I will also present more recent results that we have been obtaining. In particular, we will focus on the stellar mass and luminosity functions that we have constrained in a paper that we have submitted a couple of months ago. And finally, I will present the current work and the ongoing projects that we have here about the stellar population systems for the future. Okay, so let's start. As many of you know, during the last decades, there is an increasing number of large-scale multi-filter surveys, especially in the optical range, that are demonstrating to be an excellent, to provide an excellent set of data to study many different topics in astronomy and astrophysics. In fact, this kind of surveys present really nice advantages to take into account. For instance, these surveys, there is no selection bias for them, because you are imagine part of the sky, so there is no approximation of sources. And also, typically, the flux calibration of the bands is typically very really nice. In addition, and with similar telescopes and with the same observing time, typically these photometric surveys can reach a depth that is higher than other, for instance, spectroscopic surveys. And the photometry is not affected by aperture bias, because basically for each of the sources in the images, you define the proper aperture to integrate all the flux coming from different sources in the images. And also, typically from images, it's very easy to get photometry for each of the pixels of the sky that in some cases can be very interesting for especially research studies. And also the most state-of-the-art multi-filter surveys, like the case of JPAS, are including a large set of narrow bands, and this kind of data is halfway between classical photometry and low resolution spectra. So for this reason, we used to call this kind of data G spectrum in the collaboration. So due to the configuration of this multi-filter service like JPAS, the possibilities that we have to explore many topics in astronomy is really large. And here, for instance, I mean, just to illustrate this, I'm showing the kind of working groups that we have in our collaboration that you can see that is can be very different, ranging from cosmology to star transients and galaxy evolution studies, as is my case. I'm not going to give all the details about this. And in our particular case, we are interested in the stellar populations of galaxies. So right now, during the last years, we were exploring the potential of JPAS-like surveys in order to perform stellar population studies of galaxies. And also, we were working and preparing all the techniques and methodologies for this kind of data. So, first of all, I'm going to give a very brief introduction to the JPAS survey, or the JPAS survey. So basically, it's as I said, it's a large-scale multi-filter survey that started in the last October 2023, and is planned to observe in the optical range an area larger than 8,000 square degrees. That is going to mainly observe the northern sky hemisphere, but also is going to serve a small part of the southern one. So the survey is carried out from Observatorio Astrophysical Javalambre in Teruel, Spain. Here we can see a picture of the telescope that is going to carry out the imaging of this survey is here you can see that the most important features of for the telescope and for the observatory. And here is just to illustrate the JPCAM, which is the instrument that is going to observe this survey, which is mainly composed of 14 360°, and as you can see, the field of view is very large. Also, you have many more details here in the web, also here in these papers. So the main characteristic of this survey is the photometric system. As you can see here, it's composed of 54 narrow bands with a full width half maximum a bit lower than 150 angstroms that were complemented with two broad bands, well, actually two intermediate bands in the blue or in the red. And also it includes 4 slow-like broadbands. So given the peculiarities of this photometric system, one of the key goals of the project is to determine precise photometric resistance. With this photometric system, we expect to get more than 100 million galaxies with this photometric precision, and for about 1% in precision for photometric resistance for more than 300 million galaxies once the survey is finished. So, as I said before, this survey started by the end of last year. However, we had a preliminary data set that we call miniJPAS in order to test the potential of JPAS. Also, well, this survey is called miniJPAS. You have all the details in this reference. And also, one of the goals of the miniJPAS survey was to test the performance of the telescope, as well as to perform a first scientific exploitation of this kind of data. So this the configuration of this miniJPAS survey was conceived to be as close as possible as the one for the JPAS survey. The only difference is the camera that is used for the imaging that is a bit different. It's only composed of one CCD, and for this reason, the field of view is much smaller than the one for the JPAS survey. And here you can see the footprint of the miniJPAS survey, which is centered in the Aegis field. So for this reason, it overlaps with other very well-known surveys like the Standard Crop Strip, the HSC, and also Alhambra. One of the main features that we can summarize here for the miniJPAS survey is that it also was observed using the same photometric system than expected for JPAS. The completeness of the detection of the catalogs for galaxies is up to magnitude 22.7 for the year one, and for point-like sources, this completeness limit is at 23.6. The total effective area of the survey is a bit less than 1 square degree, and we check it in the paper by Caballero et al. 2021 that the precision for the photometrics is already achieved for the miniJPAS survey. So, in order to perform our stellar population studies, well, it's also worth mentioning here that in the rest of the slides, all the results that I'm going to show were obtained using real data from the miniJPAS survey. Okay, so in order to constrain the stellar population properties of galaxies using this kind of data, we have been developing tools, and in particular, in my personal case, I was putting a lot of efforts in the development of SED-fitting techniques in order to constrain the stellar population properties of galaxies. In my case, I'm using the SED-fitting code MAFIT, which is the code that I started to develop during my PhD, but also in our stellar population group, we have another SED-fitting code that is called deg². And basically, as you can see, these SED-fitting codes have a lot of common features, and the main differences are in the models that we use to constrain the stellar population properties of galaxies. So for MAFIT, we are using a non-parametric star formation history, in particular a two-vast model, and basically is using a parametric star formation history for building the models. One of the things that I have been working in the last years here, since I started my several postdoc here, is that also MAFIT is including as another free parameter the photometric physics, and also including the uncertainties in the determination of this parameter to perform the SED-fitting analysis of galaxies. Here, for instance, we can see a case of the probability distribution function of a photometric receipt of a faint source in miniJPAS. And you can see that in faint sources, in general, these functions are very complex. And in some cases, in the faintest objects, also present multimodal distributions that you can see here. In this case, the 3 peaks, but as I said, is a very faint galaxy in miniJPAS. But the code for a general case is also including this information during the SED-fitting analysis. And as a result, from the SED-fitting, we can obtain also luminosities for all the bands, stellar masses for the galaxies, reference colors, age metallicity, extinction, and also all these parameters with uncertainties and correlations. And also during the next slides, all the results that I'm going to show are based in the result that I obtained with my SED-fitting code. So here I illustrate 2 SED-fitting cases of 2 galaxies, of 2 real galaxies from miniJPAS that we obtained with with math it in red, and in black is the photometry from the catalog. And you can see that for this panel it's a fitting result for a luminous red galaxy at redshift 0.55 in miniJPAS. And it's interesting that even at this redshift we can get a very nice photometry that allow us to see some of the typical spectral features that we can expect from this kind of galaxies. For instance, we can see the magnitude band, we can see the 4000 break, also the G band, etc. And just to illustrate this and the quality of the results, for this luminous red galaxy we obtained that is typically old with an age close to 9.8, is supersolar metal with a supersolar metallicity, low extinction, and here you can see that is also very massive. And on the right panel, it's a more noisy case, but it's to illustrate that even for emission line galaxies with very low stellar mass, up to redshift 0.25, sorry, we are able to provide a good fit to the continuum of the galaxy, and also we are able to detect emission lines. In this case, here we have H alpha, and here we have O3 and H beta. And expected for this kind of galaxies, the age is typically below 1 gigayear. Subsolar metallicity's extinction is larger than for quasar galaxies, and the stellar mass is very low. So, also using our SED-fitting results, we performed a first study about the stellar content of the galaxies in miniJPAS. We did this in the work by Rosa González Delgado et al. 2021. And in this case, we studied the reliability and the consistency of the results in order to characterize the uncertainties and the stellar populations properties of galaxies using this kind of data. Here, for instance, just to illustrate, we see the stellar mass versus color correction for extinction diagram, okay, in order to check all this. And we see that depending of the position that galaxies lies within this kind of diagrams, the positions are very correlated with the stellar population properties of galaxies. Here on the top, we can see the so-called recent galaxies, and here in the bottom, we can see the star-forming galaxies. So, for instance, we found that the typical properties that we can expect from other stellar population studies. For instance, the correlation between the age and mass, the correlation between metallicity and mass, and also the typical parameters that we obtain for quasar galaxies that are typically more massive than the star-forming ones. For instance, in the nearby universe, they are typically old, and metallicity, the metal content is also typically larger than in star-forming galaxies. But also, within the collaboration, we performed another test, and we explored if we were able to determine the cosmic evolution of the star formation density of the universe using galaxies from miniJPAS. In this case, we selected galaxies in this redshift bin, and using the results that we obtained from our SED-fitting codes for this exercise, also in the collaboration, we are 3 active groups working on this in this moment, and we have 4 SED-fitting codes. For the 4 SED-fitting codes, we found that the cosmic evolution of the star formation rate density that we obtained for the same sample of galaxies in all the cases was compatible with other previous spectroscopic studies and from the literature. So in something that also I was working in the last year, sorry, it was that I was trying to find a method to perform a classification of galaxies, a spectral type classification of galaxies, only using this kind of data without using any kind of spectroscopic data or whatever. So in the beginning, we started to explore, for instance, the well-known color diagrams or the star formation rate versus stellar mass diagrams. And in particular, we found that it was very interesting and very efficient to perform this classification. And the best candidate that we found using the miniJPAS-like data, it was the stellar mass versus color diagram, but the color is corrected for extinction. Okay? So making use of this diagram, we were able to determine a color limit as a function of the stellar mass, as a function also of the redshift, in order to perform classification of galaxies as a function of the spectral type. Here, for instance, we have the plot that we obtained in that moment that is also included in the presentation paper of the miniJPAS survey. And we found that it was very reliable and very effective in order to determine this spectral type classification. Also, more recently, during the last years since I arrived here at the Instituto Astrophysical Andalucía, I also worked in improve a bit more this diagram. And for instance, my aim was to assign also probabilities to this classification, okay? Because as you know, the stellar masses, the red spring colors, also even the redshift, typically include uncertainties in the determination of these parameters. So typically here are not plotted, but there are error bars that in some cases tell you that the classification is not so clear. So for this, I developed a method to compute this probability, and depending of the position of the galaxies within these diagrams, also taking into account the correlations among all the parameters and the errors, we assign a probability to be quiescent or to be star forming. So here I plot these probabilities. The bluer the probability is lower, okay? So that means that the probability is higher as to be a star forming galaxy. And on the other hand, when the redder, the more quiescent is the galaxy, and the higher is the probability to be a quiescent galaxy. And here is easy to see that when we are close to the color limit that is detailed by this equation, the probability tends to be close to 0.5. So in principle, this classification is working very well, and later I will show why. So also for the collaboration, it is very interesting to for the collaboration and also for our aims to study the stellar population of galaxies. It's very important to define the completeness or the limits of our samples, especially because these samples are flux limited samples, which means that the proper flux limit is introduction of bias in the selection of our galaxy samples. So for a proper determination of these limits, we developed some techniques that or some methods that were originally based on the work by Posetti et al. 2010. But we were working a lot in order to improve these methods, and also we parameterize we provide analytical functions in order to determine the completeness limits for stellar mass and for luminosity also, as a function of redshift for any completeness level, and also depending on the limit that we use to define our flux limited sum. Here, for instance, to illustrate all this, we are well, also it's worth mentioning here that we perform this analysis for star forming and for quite some galaxies because of obvious reasons. Because typically samples of star forming galaxies are deeper than the quasi ones. And here, for instance, we illustrate for a flux limited sample or for a magnitude lower than r equal to 22. This will be the completeness limit of the sample from miniJPAS. The dotted line will be for 50% completeness level, and the dotted line for 5%. And these are the completeness limits for stellar mass, for star forming, and for quasar. All these details are there in the paper that we submitted a couple of minutes ago. So also within our stellar population group, we aim at developing a methodology in order to determine the luminosity and the stellar mass functions of galaxies. And the idea was also to include all the results that we were obtaining with all the information that we were obtaining from our SED-fitting analysis. So when I arrived here, I started to develop these methods, and the method is based in the so I mean it determines the stellar mass and luminosity functions, and in particular is based is fitting the sector function that typically are very well known in astronomy. As you know, these parametric luminosity and stellar mass functions depend on three parameters. That is the characteristic luminosity, the characteristic stellar mass. These coefficients alpha and beta are related to the faint end slopes of the functions, and also the normalization, where the normalization provides the typical number density of galaxies. So in order to perform all this analysis, there is a large set of inputs that we need. So for instance, we need the area of the footprint, that in our case is 0.9 square degrees for miniJPAS. Also, we need the photometric redshift in order to perform the SED-fitting analysis. We also need a star galaxy classification, okay? Yeah, because we are interested only in galaxies, of course, because these are the luminosity and stellar mass functions of galaxies. And we use the fluxes for all these sources in order to perform the SED-fitting analysis. And also, we studied these functions as taking into account the spectral type classification of galaxies, which is very common for this kind of studies, because as I showed later, these functions typically evolve differently depending on the spectral type of the galaxies. We also needed the stellar masses and reference luminosities for each of the galaxies, which in this case were obtained using the SED-fitting code MAFIT. And we also needed the luminosity and stellar mass completeness that I showed in the previous slide. So here, this plot is just to illustrate the typical uncertainties for the luminosities and for stellar masses that we are obtaining in the JPAS survey right now. So as you can see, these uncertainties depend on the spectral type and also depend on the right of each of the sources as expected. So typically, a larger redshift uncertainties are large as expected, and also we found that for quasi-distant galaxies, uncertainties are typically lower than for star-forming galaxies. So the method that we developed in order to constrain the stellar mass and luminosity functions is based on a maximum likelihood method, for which we also use Monte Carlo Markov chains method for sampling the posterior distribution, which is shown here. And we introduce that the fainted slope, the characteristic parameters, and the normalizations are linear functions with redshift. Also, we introduce a term that controls the star galaxy classification, the spectral type, the completeness, and many other features, and also typically the quality of the photometric redshift and many things of interest for this. And finally, also this method, owing to the distribution of errors that I showed in the previous slide, we found needed to correct these luminosity functions for editor bias effects. So here, this is the typical corner plot that we obtain for the determination of in this case, for the stellar mass functions of quasi-distant galaxies. You can see here the parameters that we found and the uncertainties for each of the parameters. And here in the posterior distribution, these dashed lines illustrate the 68% level. Okay, so finally, after doing all this analysis, here on the left, we can see the luminosity luminosity functions for star-forming galaxies, and on the right, the luminosity functions for quasi-distant galaxies in the miniJPAS survey as a different redshift. Okay, as you can see, and finally, what we found as also as something that is very well known that from previous studies and from much deeper photometric surveys, that the slope of the luminosity function of star-forming galaxies is very constant, since redshift more or less 1, and the changes for these functions are typically concentrated in the right end of the functions. And here is the same, but for quasi-distant galaxies, as it was observed in previous surveys, the evolution of this function changes more than for the star-forming case. Okay. Also, solid lines illustrate the luminosity ranges for which the miniJPAS survey is complete, and dashed lines correspond to the part that is not complete. Now this is the same, but for the stellar mass functions. Okay, again for star-forming galaxies and for quasi-distant galaxies on the right. And solid lines, you can see that as for the luminosity functions, the stellar functions of star-forming galaxies are typically constant at the front end, in this case for the less massive end of the stellar mass functions, and there is typically an evolution in the high mass end of these functions. And also for quasi-distant galaxies, as is well known, at decreasing redshift, there is an increasing number of quasi-distant galaxies in the most massive part. Okay, but also there is a much more remarkable effect in in the less massive part, in which we found that the number of quite-thin galaxies with stellar masses below typically 10 to the 5 increases at decreasing redshift. So also here is remarkable that the effect of the Eddington bias, okay, these lines here illustrate with how would be the stellar mass function that we obtain for star-forming galaxies in the case that we don't correct for Eddington bias. And solid lines are illustrated after correcting for Eddington bias. Also, this effect here is less clear because there are a lot of lines that overlap each other, but also the effect is very, very important. Also, it's interesting to obtain many times to obtain the fraction of red galaxies that we can typically obtain in galaxy surveys. For this fraction of red galaxies is very easy to obtain once we have determined the stellar mass and the luminosity functions. So basically, if you divide the stellar mass and luminosity functions of galaxies between the total of galaxies in the sample, you can get these plots here. And typically, as I expected, at since redshift 1 more or less, the more massive galaxies are typically quite thin galaxies, and for less massive galaxies are typically dominated by star-forming galaxies. So here is again the luminosity function and the stellar mass function of star-forming and quite-thin galaxies at different redshifts, but now we are comparing our results with other results from the literature from deeper spectroscopic, from deeper photometric surveys, and also we include results from the spectroscopic surveys, and we can see that typically they say for all the functions and all the at any redshift are reproduced with the results that we are obtaining using galaxies from miniJPAS. And this is the same, but in this case, what we are showing is the stellar mass functions of galaxies, but also we are getting very nice results. Another interesting parameter that we can compute from the stellar mass and luminosity functions is the cosmic evolution of the stellar mass density and the cosmic evolution of the luminosity density. Okay. As before, here we are also confronting our results with the results from the literature, and we can see that for both spectral types, we are obtaining results that are well reproduced, but by other surveys. In blue is for star-forming, in red for quite-thin, and black, the black line illustrates the total population of galaxies. And as obtained by previous surveys, what we are getting is that the luminosity density decreases at decreasing redshift. And about the stellar mass density, we find that this one is increasing at decreasing redshift. And also, we find that typically the stellar mass density that we find in star-forming galaxies is close to no evolution, and this evolution is dominated by the quite-thin population. And this plot is just to illustrate the results that we are obtaining with the method that we developed here since I started my postdoc here, in comparison with the results that we will obtain using the traditional methods, for instance, the Sandwich method or the Vmax method. using only traditional methods, we are very limited in order to determine, in this case, the cosmic evolution of the luminosity density. And above redshift 0.4, we will obtain that these parameters are very, very effective. And this will be the same, but now for the cosmic evolution of the stellar mass density. So now this is the last part of the seminar. And here I'm going to briefly introduce the tool that, in this case, my PhD student Julio is developing here as part of his PhD here at the Instituto de Astrofísica Andalucía. And it consists in a tool that is planned to study the distribution of the stellar content of galaxies, in especially resolved galaxies that were observed in photometric surveys like JPAS. So this tool is divided mainly in 4 stages, 4 parts, okay? And because it's planned to be also an automatic tool, that in the first step, for a list of candidates that are especially resolved in the photometric catalogs, it takes a stamp or an image for each of the bands of the survey to subsequently apply a PSF homogenization of the images for each of the bands. Okay? So here we see the original image in the R band, and here we see the image after the PSF homogenization, where in this case we are taking the worst PSF that we found for all the bands. Okay. This step is very important. We found that this step is very important, especially when we want to determine the stellar population properties of galaxies in the most inner regions of the galaxies. As we can see here, before the homogenization will correspond to the red dots that we see here. Okay, these are magnitudes versus the effective wavelengths for each of the bands in the miniJPAS survey, and this will be the photospectrum after the PSF homogenization. But it's also true that when we explore the set of the different regions of the galaxies, when we are in the outer regions, the PSF homogenization is less relevant than in the very inner parts. So finally, not finally, but later, after the PSF homogenization, also this tool masks all the sources, including foreground and background sources, with respect to the galaxy that under study, in order to provide the correct photometry for different regions of the galaxy. So now, finally, we are exploring different methods in order also to define regions for each of the spatially resolved galaxies. Right now, we started to work with elliptical apertures, and this tool finally extract the photometry for each of the regions. Okay, and later, once we get this photometry, we send the photometry to our self-fitting codes in order to determine the stellar population properties for each of the regions. And this way, we are able to analyze the distribution of the stellar population properties of these galaxies. So here is just to illustrate one of the results that we are obtaining. In particular, in the miniJPAS survey, there is a galaxy that is also included in the MANGA sample. And here we illustrate the stellar mass surface density of a stellar mass that we obtain using this tool. And I don't know if you can see here these star-shaped markers illustrate the values that were obtained for the same regions for MANGA. And also this is to illustrate that the potential of this kind of studies, because here with MANGA, you can more or less determine all the parameters up to one effective radius, but with the JPAS images, in this case, we were able to extend this profile up to an effective radius equal to 3. And taking into account that once JPAS is complete, we plan that we can resolve stellar population properties and ionized gas distribution of galaxies up to between 2 and 300 radius, but for more than 100,000 galaxies. And also, these are very preliminary results, but basically just to illustrate the typical radial profiles for different radial profiles for stellar population property that we are obtaining for a subsample of 24 quasi-stellar galaxies that are more massive than 10.7 solar masses. And we can see that for these cases, we are obtaining that the typical radial profile for 4A is close to be flat, as it was measured in previous surveys. The inner parts of massive quasi-stellar galaxies are typically solar and supersolar metallicities, and in the outer parts, these values decreases down to solar metallicities. And typically, these galaxies are 7% emission line, 7% emission lines. Okay, so this is the last slide. Here, summarize here all the takeaway conclusions that I presented here today. So just remind me that we are ready to perform very potential stellar populations with the ongoing JPAS survey involving stellar population properties. And also it's very interesting that in the future we can explore also these properties in terms of environment and radial profiles. And as the JPAS survey has started, we expect to do all this in a very good future. So thank you very much.
Thank you. So now it's time for questions. So for people in the room, please speak loud so that people in Zoom can hear you. And for people listening soon, if you have questions, please raise your hands. So who wants to start?
Can you show us again, the beginning of your talk, the plot of was U minus R versus the mass of the galaxy? Oh, this slide before.
This one?
This one. I'm not an expert in the subject. I have to figure out what does this plot mean. I mean, there are two bulks of data. One, the biggest one, see the lower part of this diagram, and another one over there. Yeah. What do they mean?
This is the density of sources here.
Sorry?
The density of sources in the plot.
Can you speak louder, please?
Sorry, is the density of sources in the plot. This means that there are more sources here than in this part.
No, okay, I've got it. But why are those two bulks of data? They have different, distinct colors, especially.
Yes.
They differ by one order of magnitude, but they differ mostly from their colors. Why is that?
This is because star-forming galaxies are typically 4 times more frequent than quasi-stellar galaxies or galaxies in the red cloud versus the galaxies in the blue sequence.
Okay, so in the slide, in the next slide, this gap doesn't appear. Here.
No, because I'm not plotting these levels here. Here we are illustrating the probability of these galaxies, but it's the same plot.
Okay.
So here is you plot again the density curves of galaxies. You will see that here also there are many more galaxies in this region than in this region. Typically, it's a factor of 4.
Thank you very much for your talks. I think very interesting to me. It's stellar, but here we are talking about something very similar to what we find over the stellar population. But coming back to the previous slide, well, so here it is supposed there is not previous bias in the selection of galaxies. No? So it is the typical snapshot of the galaxy population in this redshift interval. And coming back to the next one. All right. So what do you tell me here? What kind of methodology do you use for obtaining the probability?
Well, the probability is computed from the change of value that we get from a Monte Carlo simulation for the SED-fitting analysis for each of the galaxies. So just get a set of photometric redshift values, a set of stellar mass values, and a set of Gaussian colors corrected for extinction. Okay. So what you get is okay, that having all these, basically this change includes the correlations and uncertainties. Okay, so from there is a fraction of points or of simulations that are going to be above this limit that depends on stellar mass, redshift, and color, and there's another fraction that is below this region. I think that this region is not a line; it's a plane. Okay. So basically, you isolate what's the fraction of probability that is above and the fraction of probability that is below.
Okay.
When you show the velocity and mass functions as compared to other results or the previous results, those notes you said, I think you said that they are comparable, but in the for the for the fainter galaxies, in some cases, we can see that the triangles are quite a bit different from the other ones. So could you explain that, please?
Well, these are the results from beepers. So I think that the main difference is because the completeness limit of beepers. So basically, they only fit the most bright part. And basically this component, well, this part of the cube is more or less free, let's say. However, when you include results from much deeper surveys such as Cosmos or Alhambra, also for stellar masses, we don't have the functions from beepers. Oops, sorry. But typically, when you compare the results with much deeper results, typically everything is more or less in the same area, let's say, except deeper.
Can I ask another thing? Do you think it could be possible to somewhat anchor what you get here from so many filters with the upcoming very deep surveys that will be done with just several filters, as the case of probing?
So you mean to do the same, but for deeper surveys with less bands?
You cannot do the same because you will have just 4 or 5 filters, but in some way try to anchor what you get here from what you would get from a much smaller number of filters and broader filters, and try to do something.
In principle, if all the errors or the probability distribution functions and all the correlations are well determined, yes, because basically this is a probability analysis. I mean, you're going to determine the surface with the highest probability that reproduce your sample of observation, let's say. But it's true that what we found is that it's very important that all the probability distribution functions are very well determined and the correlations are also very well determined or are real, let's say.
Well, thank you, Luis, for the great talk. I just as a comment, maybe you can elaborate why the evolution of the properties and luminosity. So are you doing until 0.7 redshift and no more or less? And what the significance of this is? This is because of the survey, but can you elaborate more? And what is the significance of this in relation to the evolution you see? Whether there is a monotonous evolution, or is the on mass functions going towards one, or do you notice something critical near 0.8, something like that?
It's a completeness. Because the completeness above redshift 0.7 is around here. So basically you have a few galaxies here that the only the only impact of these galaxies is that they introduce a lot of noise here. So I found that it's not necessary to go much at higher redshift, because basically there is no information to constrain anything. And the fit is very well determined at lower redshift, because the information that galaxies at even here maybe is more clear. At higher redshift, they are only saying a bit here, but the rest is completely uncertain, because you don't see the galaxies, you are not including galaxies in your sample. So that's the reason. Also, it's because the number of quiescent galaxies start to decrease very fast at redshift higher than 0.7. So basically, maybe you are around here. Okay.
Yeah. So but this is nothing critical in 0.9, something like that, or you expect something, so it is smoothly.
No, also you can see here, for instance, okay, for luminosity functions in more easy. You see that still you have galaxies here. Okay, this is 0.8. But for stellar mass is more critical, and some of them start to disappear here. And for quiescent galaxies, basically about 0.8, 0.9, you have a dozen of them.
Good, thank you.
More questions? Okay, if not, so let's thank Luis.